Hello and welcome back. I'd like you to recall from some previous lectures that we defined velocity as a vector quantity that has a magnitude and a direction. Acceleration we defined as a change in the velocity divided by the time over which the velocity changes. So acceleration then is the change in either the magnitude or the direction part of the velocity divided by the time. So there are two different ways that we can change the velocity. Therefore, there are two different types of acceleration. We could experience a change in just the magnitude part of our velocity, i.e. changing our speed, or we can change the direction part of the velocity, and that is changing our direction. Like if we're in our car, that would be using our steering wheel. And we can simultaneously change both of those. We can be speeding up or slowing down as we are turning the steering wheel. So we can change either the magnitude and or the direction part of the velocity and yield both types of acceleration. So let's define these two different types of acceleration. So there's one type that's called tangential or linear acceleration, and it's going to get the symbol a sub t. Recall a is the symbol that we use for acceleration, but now we're going to put a subscript because we have two different types of acceleration that we need to clearly distinguish. So this is t standing for tangential acceleration, and it's the change in the magnitude part of the velocity divided by time. So that's taking care of changes in magnitude part of the velocity. The second type of acceleration that we're going to distinguish now is radial or centripetal acceleration. The word centripetal means center seeking from the Greek language. So center seeking, centripetal, the acceleration will get the symbol the little subscript c to remind us that that's centripetal acceleration. So these are the two different types of acceleration that we need to distinguish. This acceleration keeps track of changes in the direction part of the velocity. So change in direction part of the velocity divided by time. So recall that acceleration itself is also a vector. So in other words, this tangential acceleration will have a magnitude and a direction, and the centripetal acceleration will also have a magnitude and a direction. So when we specify anything that is a vector quantity, we always have to keep in mind that we need to be expressing both a magnitude and a direction. So what kind of directions are we going to have as possibilities for the tangential acceleration? Well, the tangential acceleration, a sub t, will always point either in the same direction as the instantaneous velocity, or in exactly the opposite direction. As the instantaneous velocity. And it depends on whether the object is speeding up or slowing down as to which of these scenarios it'll be in. So if the object is speeding up, if delta v is greater than 0, in other words, the object is moving faster each successive second than the second before it, then a sub t points in direction of v. Okay, if instead the object is slowing down so that delta v is less than 0, and we're just talking about the magnitude part of the velocity, so let me just get rid of this little arrow here. So if delta v is less than 0, then the object is slowing down and the tangential acceleration points opposite to v. So it either points with v or against v depending on whether the object is speeding up or slowing down at that point in time where you are looking at the tangential acceleration. So those are the only two possibilities. So let's consider an object that is actually moving in circular motion. So here is an object that is moving through a circle, and let's say it's moving in this direction or in this sense, then the object at different points is going to have different tangential accelerations. So for example, right here, instantaneously the object is moving to the right. That would be the direction of the velocity. At this point right here, the object is instantaneously moving down. At this point right here, the object is instantaneously moving to the left. And at this point right here, the object is instantaneously moving up. So the object is continually changing direction. And remember, the magnitude part of the velocity is indicated in the length of the arrow. And so I've drawn these arrows to be roughly the same. So in this case, there would be no tangential acceleration. But let's compare that with an object that is moving such that its velocity at the top maybe is got this magnitude, but then at this point right here you can see that the object has sped up. So what direction is the tangential acceleration at this point? Well, since the object is speeding up at this point, then the tangential acceleration is going to be in the same direction as the velocity. Notice that here the tangential acceleration will be 0. Again, that's just looking at the lengths of these arrows. They're the same length. That means the magnitude part of the velocity is the same. Tangential acceleration either points with or against the velocity's instantaneous direction, depending on whether the object is speeding up at that instant in time or it's slowing down at that instant in time. Centripetal acceleration gets this, or radial, and you'll see some texts use a sub r instead of a sub c. The text we're going to be using is a sub c, so we'll stick with that. But centripetal means center seeking, and that's because the direction part of the radial or centripetal acceleration always points into the center of the circle that the object is moving through. So a sub r, a sub c, always points into center of circle object moves through. And even if the object is not exhibiting exact circular motion, but is instead moving, let's say, through some kind of a path in which the direction is changing, then each and every point on this path as the object moves through will have an arc that belongs to some circle with a radius r. So let's say this piece right here is this part of the track right here that the object is moving through. This arc right here belongs to a circle, which I just drew, and here's the center of the circle. And so at this point right here, the centripetal acceleration is going to point into the center of the circle. So that's going to be the direction for AC. If I come back over to these circles we drew earlier, you can see that this object is moving in circular motion. And so everywhere that the object is on this circle will have an acceleration that is centripetal that points directly into the center of the circle. So those are all the directions for the centripetal acceleration. And so we can find the direction part of the centripetal acceleration by just knowing where the center of the circle is that the object is moving through. The magnitude part of the centripetal acceleration is well defined and is always equal to, so this is just the magnitude part of the centripetal acceleration, the linear speed squared, how fast the object is moving squared, divided by the radius of the circle that the object is moving through. So in our cases back over here, this would be r, this would be r, the radius of the circle. So I would calculate how large the centripetal acceleration is, i.e. how long I should make these arrows, by just taking the speed that it's moving at, squaring it, divided by r. Notice that the centripetal acceleration here is changing on this circle because the magnitude of the velocity is changing from this point to this point. But here, the velocity remained constant, and so the magnitude part of the velocity remained constant. And so what that means then is that the magnitude part of the centripetal acceleration will remain constant. But note that the direction part of the centripetal acceleration will not remain constant. It changes in direction by 360 degrees every time it completes one full revolution. So this type of motion we're going to be referring to where the magnitude part of the velocity remains constant. So magnitude of v equals a constant for this circle. We're gonna say that this is going to be called or referred to as uniform circular motion. So this is uniform circular motion. So that's when the magnitude of v is constant. Okay? So we will pick up here next time with applying these concepts to some problems to solve so that we can build those nuances in our head. All right, we'll see you next time.